Thanks, Miguel. So my topic's new tools for fire weather forecasting, and my co-authors are Robert Fawcett, who's in the room, Will Thurston and Kevin Torrey. Andrew gave us a very nice introduction in which he spoke of the many anniversaries, and one of the significant ones is that it's 30 years since Ash Wednesday. And so I thought in preparing this talk, it's always nice to look back before you look forward. I'd start by looking back at the forecasts that were issued for Ash Wednesday. So the morning before, this is the 11 a.m. issue, warnings nil, continuing dry and warm to hot in the north, no mention of very hot with light winds, and so forth. Fire danger generally high to very high. If we go to the afternoon issue at 5 p.m, there's now a fire weather warning for extreme dangers in the Mallee. That's the northwesternmost tip of Victoria. Warm to hot, light to moderate. We've got up to moderate northwest winds, milder sea breezes. The issue on the morning of Ash Wednesday. We've got two warnings. The most important one's obviously the road weather alert, but after that we have the fire weather warning, and we've now got extreme dangers in the Mallee, so again up in the northwest of Victoria. The state forecast is still mentioning light winds tendering moderate northwesterly. Fire danger, high to very high, rising to extreme in the northwest. 9:30 a.m, the forecaster's got a bit nervous and put out an amendment. Forest fire danger will be extreme today in the Mallee, Wimmera, Western and Central districts. So that's the western third of Victoria plus the bit around Melbourne. The 11 o'clock routine issue, fire weather warning, extreme in all districts. I suspect by that time of day it probably was up over 50 in all districts. You really get the sense that the forecasters were playing catch-up. The significant wording here, if you read the body of the forecast down there, that's the first occurrence of the word change in the forecasts at 11 a.m. on the morning of Ash Wednesday. The evening issue, fire danger extreme tonight with and ahead of the change, and we've now got dry and hot. First mention of dry in the forecasts. Strong to gale force, which is a bit more than the light, which was mentioned the previous day, and so forth. So, you know, it's sobering to look at these, and it's easy to laugh, but this is only 30 years ago. I joined the Bureau exactly a year to the day after Ash Wednesday. So many of us in this room actually remember the event, and I think the fact that we're laughing gives us some indication of how much things have changed. Black Saturday. So this is the extended outlook that was issued 1 week before Black Saturday, so this was issued Sunday, and the bit down the bottom with the red arrow, trough should deepen, da-da-da-da. This day is tricky. I love that. I must find out who wrote it. But it's actually a terrific forecast in all seriousness, because it is giving an indication that there is uncertainty in it. If you read further down it, we could get very hot northwesterlies, and further down, this day has the potential to be a problem day for fire weather. Now obviously the forecasters were not certain at this point, but they recognised the possibility, and within the realms of possibilities, this was going to be, if there was going to be a bad day in the next week, this was going to be it. Issued Wednesday, 4 days beforehand. We have a very different product, don't we? It's nicely graphical, it's not some scungy telex, it's got some nice coloured maps, wind changes on the maps. I love the bit up the top right, the absolute extreme fire weather spike day. I went back and read a whole bunch of these, and I really got the feeling that the forecasters were running out of adjectives and that we should find a thesaurus. But if you look at the important detail, both FFDI and GFDI above 50 will be reached in the morning from 9 a.m. onwards. It's enormous wealth of important detail. Poor relative humidity recovery overnight due to the warm temperatures, and the fact that the change will be initially dry and gusty. And as we remember, the forecasters were confident enough at this point that we actually got the State Premier involved in communicating the risk. The other thing that's significant about this that I'd like to draw your attention to is look in the bottom right-hand corner. It's actually issued by 3 agencies, so it's not just the Bureau acting alone, and I think that's one of the big bits of progress, the way that the Bureau and the emergency services and fire agencies work together these days. So what's changed? How have we managed to get so much better? Well, there's a bunch of things. Improved observations, improved analysis and prediction, better understanding, better means of communication, better ways of actually turning the data into usable forecasts. That bottom one is a slide from the GFE, and we've got better at verifying our forecasts too, which is also an improvement. And we'll look at a couple of these things in detail. Numerical analysis and prediction, the computer models, has become really critical for modern weather forecasting. And this is a diagram of forecast skill according to one metric, higher numbers are better, for the northern and southern hemisphere over the last 30 years. And in each case, the bottom curve of the pair is the southern hemisphere, the top curve is the north. Steady improvement. We've got about an extra 3 or 4 days of predictability, which means that your 5-day forecast that we issue today is about as good as the forecast for tomorrow was back in the days I joined the Bureau. It's not bad for one guy's career, is it, to see that much improvement? We've also seen a closing of the gap between the northern and southern hemispheres. The northern hemisphere has more land, more people, therefore more observations, but it's actually the use of satellite data that has led to the closing of that gap. Satellite data and better techniques for using the data. And, you know, the 7-day forecasts are pretty usable these days, and the 10-day forecasts are not getting far off it. The models are getting very close to reality. Phil told us this morning that he doesn't like statistics, so rather than a chart of statistics, one of those is a real satellite image of Cyclone Yasi. The other one is a 48-hour forecast from our Access NWP system, valid at the same time as Cyclone Yasi. And you can tell me afterwards which one's reality and which one's the satellite picture. So to move to fire events, this is from a simulation that we did as part of our Bushfire CRC research. This is Black Saturday, beginning the night before. We're now coming through the morning. The sun is up, we're heating rapidly, that's temperature and wind vectors. Here comes the wind change from the southwest. You can see the vectors ahead of the change have got the jitters. Talk about that in a minute. The other thing you can notice is that there's actually a few wind changes on this chart. We've got some changes propagating through here in the evening, and then we've got a patch of strong winds pushing to the south here. Now we've got the days warming up, and here comes the main change from the southwest starting to become mobile. But notice we've got another line extending out to the west here, and there's in fact another weak wind change down here near Winchelsea. A lot of complexity going on in this forecast. One of the things that's happening that's potentially quite important, I talked about the jitters in the wind direction. If we take a snapshot, this is up over the northern plains of Victoria, of surface streamline, you can see on the left that we've got a huge variation in wind direction at the surface. And the colour shading is showing the updraft. So we're getting updrafts of up to about 5 metres a second, or close to 20 kilometres an hour, being produced by these features. That is a strong enough updraft to help suspend bark. And so we wonder whether these natural features, which there's actually good observational evidence for on the day, contributed to some of the spotting. Once the plume got the spots up to 1 kilometre or so above the surface, the updrafts in the boundary low rolls were able to continue to hold them up and transport them further. That's one example of small-scale phenomena, stuff that's only a couple of kilometres across that can affect the fire. And I should have said another way that those things affect the fire is the variation in wind direction, of course, causes the fire to spread laterally, which makes the head fire wider, and as Phil told us this morning, that means that the fire will propagate faster. Another example where small scales were important was the fire in Margaret River nearly 2 years ago. These are images of the surface wind speed and on the left and dew point temperature, measure of humidity on the right. Red is strong winds and dry air in respectively. Over on the right you see the humidity is actually very low for that hour of the morning, and what happened was from about 3 a.m. in the morning a mass of dry air was effected in from the northeast over the fire ground, which is that little black outline almost exactly in the centre of the image. At about the same time we started getting downslope winds off a small hill that was located within the fire ground, and if you look at the image on the left, the strongest winds anywhere over land are exactly coincident with the fire ground. The prescribed burn broke its boundaries at about this time, and it then burned southwards over the next 2 days, destroying or damaging some 50 houses. Fortunately, no loss of life. A cross-section through it shows the strong downdraft. The top panel is the vertical velocity, and the wind is blowing from left to right, and you can see the really strong downdraft of a couple of metres a second on the lee slope of that hill, which is bringing those very strong winds that are sitting up at about 600 or 700 metres above the surface in the bottom panel down to the surface. Resolution is important. This is what our operational global models showed for that site. This is actually about 5 or 6 times the resolution that we had for models on Ash Wednesday. The highest resolution we run operationally, you're really not seeing anything particular at that fire ground in the centre of the image. It's not until you get to the really high resolution that you pick up the potential for the downslope winds and the fire escape. Another example where we've done high resolution simulation, this is the Coonabarabran fire from January this year, and what you're seeing is wind speed on the left, surface air temperature in the middle, and the dew point temperature on the right. And there is an enormous amount going on in this image. You can see a wind change pushing up from the southwestern corner. You can see these patches. Perhaps look at the right-hand panel. You saw that lots of the blue air, the dry air, the moist air appearing during the afternoon. And if you look at the middle panel at the same time, should be starting to happen about now. These patches of dry air, moist air, cool moist air. They are thunderstorm downdrafts, which were observed on the day. Each of those is associated with a wind change. We tend to think of wind changes as being frontal type situations, but as they learnt in the United States recently, wind changes from thunderstorms can be just as deadly. The fire really does not care. Meteorologists might care what the cause of the wind change is, but the fire doesn't. Play count the wind change on this, and we've got the major change coming through from the southwest, but here comes a change from the north. The two collide in the top of the image, and we've got another change pushing in from the low right-hand corner on the southeast. And we've got a wind change associated with every thunderstorm outflow. There's a real push from the end user community often to make the forecast simple. All we want is a line on a map, I've been told. We don't want overly complicated messages, but you look at what's going on in this situation. The atmosphere is highly complicated, and if we were to reduce that to just a simple line on the map, we'd actually be withholding information. We'd be lying. It's difficult though. Here's a cross-section from our Black Saturday simulation. So if you look at the bottom, the map down the bottom, there's a line on that running from diagonally across it, and the cross-section is moving along that line about with the speed of the change. At the start, we've got a classic cold frontal type situation. It's like a density current, a massive cold air moving in. Sorry, I should have said the shading in the top panel is the temperature, and the lines are the vertical motion. Black is up, white is down. As we get back to the beginning and go through, you can see about now we're starting to get a nocturnal inversion forming, and the whole character of the change changes. It goes from being a density current, cold air is physically moving into, it's more like a ripple in an existing surface of cold air that's propagating across. The technical term is an undulate ball. If we look at the data, observations and the model as that feature went through Albury AWS, The pressure is shown by the two curves, and you can see that there's the double hump as it goes through, circled there. The wind direction is shown in the top, and these are plotted opposite to the normal convention. The lines are pointing in the direction the wind is blowing to. But circled, you can see where the wind change went through. The wind did not flip from being a northwesterly to a southwesterly. It flipped around, and then 8 minutes later it went back. Not all wind changes are the same, and I don't think it's hard to imagine circumstances in which the knowledge that this is not going to be your standard wind change could potentially save lives or property. So there are new things to predict. Types of wind change are updrafts and spotting potential, wind direction variability. But the other thing that we're moving towards, which I want to finish the talk off with, is how we deal with uncertainty. Now, meteorologists have done this informally for a while, and we're even starting to do it formally with the predictions of rain. And if you look at the Bureau website, you will see forecasts like the one I showed here. Chance of any rain, 60%. Weather forecasts will never be exact. I can tell you one thing about the forecast that the Bureau issues today that I can absolutely confident about. It's not going to happen exactly the way we say. And I'm sure that my successor in 100 years' time will be standing in a room like this and will be saying the forecast will never be exact. How do we deal with this uncertainty? Because the challenge is that sometimes we are a lot more confident than others. We can deal with it informally. We saw that in the example of the outlook for Black Saturday, where the forecaster described the day as tricky, and this is the problem day for fire weather. Great way of conveying that there's some risk without conveying certainty. But the direction we need to move to deal with this is to get out of the mindset of there is only one tomorrow. There is only one weather for tomorrow. You need to stop thinking that the Bureau knows what it's talking about and is only going to give you one alternative, because we don't know that certainty. We don't know to that level of certainty. There is always going to be uncertainty in our predictions. The problem is, it's not always the same amount of uncertainty. Some days we're actually pretty confident, and some days, well, I don't want to say we don't have a clue, but we're heading more towards, we would like to put large error bars on the forecast. The way we are moving towards doing this is going from using a single forecast to using an ensemble of forecasts, perhaps 50 different forecasts with slightly different initial conditions, slightly different sea surface temperatures, slightly different soil moistures even. And by analysing the range of that ensemble, we can assess how predictable is tomorrow. Is it actually an easy day or a hard day? We can give you a probability distribution. We can say that the temperature will be 42 plus or minus 3. Ensemble prediction systems have been shown to be more valuable than single forecasts. That's actually shown by economists who've measured the economic outcomes of using the forecasts, and you can make more money or save more lives by using an ensemble prediction system. They're more consistent than single forecasts. Forecasters talk of the windscreen wiper effect. The Bureau says it's going to be this, oh no, it's going to be this, oh it's going to be this, and it's swinging backwards and forwards like windscreen wipers. Ensemble prediction systems, because they remove some of the sampling uncertainty, the statistical randomness, sorry to mention statistics, Phil, but I'm sure you'll forgive me, because they remove some of that statistical uncertainty, they actually remove that windscreen wiper effect, and they make it easier for the users to plan, because the Bureau is not forever changing its mind. And they provide the tools to properly manage risk. Let's say we've got a fire running towards some outer suburbs of a major metropolitan area, and we want to know, we can see that there is a chance that if the winds are strong and the change is late, that the fire will get to those suburbs before the change pushes it away. So there's a risk there. If we deal with that risk by deploying some firefighters, we've removed the opportunity to use them elsewhere. Is the risk large enough that we lose the opportunity to use our crews elsewhere by dealing with the chance that the fire is going to get to the suburban area. Is it a 2% chance, 10% chance, 50% chance? I think you'd make different decisions on that spectrum. And if we can actually quantify that risk, we can manage the risk properly. So to get away from the sort of vague, waffly, in-principle stuff, let's look at Black Saturday again. These are forecasts valid at 11 a.m. on the morning of Black Saturday. The one on the left is the ensemble mean temperature forecast for Australia-wide. These are from the European Centre for Medium-Range Weather Forecasting. And the one on the right is the standard deviation calculated across the ensemble of the temperature forecast. And you can see that the temperature gradient is strongest sort of along the line, along the coastline from Ceduna through to Melbourne. And most of the uncertainty in the temperature is actually also concentrated along that line. So where we are most uncertain about the temperature is also where the change is, so it's where things are most critical. We can analyse those forecasts and actually calculate a change position, and this is a somewhat complicated diagram, so I'll take it through slowly. The shading, the magenta arrows are the temperature gradient. So where the arrow is large, you have a strong temperature gradient. Temperature gradient is a good way of detecting a front. The shading is the northwesterly component of that temperature gradient vector. And what I've done is I've defined the frontal position as being the maximum in the temperature gradient. The grey lines, those show, each one of those shows the front position from one ensemble member. The thick white line shows the frontal position from the control member of the ensemble. That's the central member of the ensemble that hasn't had any perturbations applied to it. And the numbers are just the standard deviation of the front position measured in degrees of longitude, I think. So there's a lot of useful information here. We can see, actually quantitatively, we can see how much uncertainty there is in the frontal position. If you were asking a question like, I've got fire crews who are working to the east of the front, what's the latest I can get them out? Here's some objective information that could help you answer that question. If you're worried about the fire burning into a community and you're worried about, is the change going to get there in time to save that community? Well, in that case, you might look at the leftmost line because that's the worst case scenario for that event. Same thing for 11 o'clock in the evening, and potentially you could get these all through the day. An opportunity to quantify and objectively manage the risk. So in summary, where have we changed? Well, we saw that slide before, so just to remind you where we started. I'd actually like to leave the last word not to me, but to some of our friends in the media. And I'll apologise, it's not a fire case, this is a tropical cyclone case. The photo is Jim Davidson, who retired last year as Regional Director of our Queensland office. And the text is from an editorial in the Courier Mail after Cyclone Yasi. Weather forecasts, like economists, tend to be pilloried mercilessly for their alleged inability to ever get a prediction right. But we still listen to them because so often, despite all the variables and the unknowns, they're often unerringly close to spot on with the forecasts. The Bureau will never get it exactly right, down to a decimal point, an hour or a few kilometres, but we come close often enough to make a huge difference. And that's really where we aim to go in the future. Partly it's continuing to move the error bars down, improve the accuracy, but if we can also move to predicting the level of uncertainty, that will enable users to make safer decisions, better risk management decisions on the data we supply. So, thank you.